Hi everyone and welcome to the computing module. In our previous lessons, we built up to a mathematical foundation using vectors, matrices, and complex numbers. But now we want to shift more towards the computer science that's needed to understand quantum computing. Before we dive into how a quantum computer processes information, we need to understand exactly how a standard or classical computer does it. At its core, your computer doesn't actually understand text, images, or video. It only understands one unit of information, which is called the bit. A bit is a fundamental unit of classical information. It exists in exactly one of two possible states, 0 or 1. Physically, inside your computer's processor, a bit is just a tiny electrical switch called a transistor. It either blocks electricity to represent a 0, or lets it flow to represent a 1. Every single piece of digital data in the world is just a massive sequence of these 0 and 1s. But since we're preparing for advanced computing later on, we need to look at bits mathematically. We can represent the state of a bit using the exact same vectors we learned about in the math module. And now let's set a simple rule. The state of being in a 0 is represented by the column vector 1, 0, and the state of being in a 1 is represented by the vector 0, 1. This vector representation is called a state vector. Right now, it might seem like overkill to use a two-number vector to represent a single number bit like 0 or 1, but introducing this notation now will be really useful in the future. But storage isn't the only thing that computers do. They actually have to be useful and do things like calculations, so we need a way to change, compare, and manipulate bits. We do this using logic gates. A logic gate takes one or more bits as an input, applies a logical operation, and then gives you an output. The simplest logic gate is the NOT gate. It takes a single bit as an input and flips it to the opposite state. For example, if you input a 0, the gate will output a 1, and if you input a 1, the gate will output a 0. Because we know that bits can be written as vectors, logic gates can actually be written as matrices. For example, the NOT gate is represented by a 2 by 2 matrix with a top row of 0, 1 and a bottom row of 1, 0. If you multiply the 0 vector 1, 0 by this matrix, then the output is 0, 1, which is our 1 vector. And if you multiply the 1 vector 0, 1 by this matrix, then the output is 1, 0, which is our 0 vector. If you want to get a little more practice, then feel free to pause the video and try to verify the calculation yourself. While the NOT gate only takes one input, most logic gates actually take 2 bits as inputs, compare them, and then output a single bit as the answer. The three most common 2-bit logic gates are the AND gate, the OR gate, and the XOR gate. The AND gate outputs a 1 only if both of its inputs are 1. Even if a single one of the inputs is 0, the output is 0. The OR gate outputs a 1 if either of its inputs are 1, or if both are 1. It only outputs a 0 if both of the inputs are strictly 0. And the XOR gate, which is called the exclusive OR gate, is slightly stricter. It outputs a 1 only if the inputs are different from each other. If one input is 1 and the other is 0, then it outputs 1. But if both inputs are the exact same, whether they're both 0 or both 1, the output will be 0. So with all of these different gates, it can be a little tough to keep track of exactly which one does what. In computer science, we map out the behavior of a logic gate using something called a truth table. A truth table is basically just a visual of what each gate does. It's like a chart where you list out all the possibilities on the left and then the final output on the right. Now let's imagine the truth table for an AND gate. Since there are 2 inputs, we have 4 possible combinations. If input A is 0 and input B is 0, the output should be 0. If input A is 0 and B is 1, then the output is 0. If A is 1 and B is 0, then again the output is 0. And finally, if A is 1 and B is 1, then the output is 1. So this is how we would write the truth table for the AND gate. If you chain enough of these simple gates together, you can actually build a system which is capable of running advanced physics simulations or graphics for AAA games. But computer scientists discovered something pretty amazing. You actually don't need all of these different types of gates. If you take an AND gate and place a NOT gate immediately after it, you can create what we call a NAND gate, or a NOT AND gate, which is called a universal gate. What this means is that by wiring together hundreds of NAND gates in specific patterns, you can perfectly recreate the function of an OR gate, or an XOR gate, or any other logical operation. You can build an entire working computer processor using nothing but NAND gates. To show this, let's try building out an OR gate using only NAND gates. First, let's remember our rules. An OR gate only outputs a 0 if both of its inputs are 0. If it even sees a single 1, it should output a 1. To mimic this OR gate, we can use 3 separate NAND gates. Let's start off with our 2 input wires, which we can call A and B. A wire is basically just a structure which can carry the information of a bit. But the nice thing about wires is that we can split them apart to basically duplicate the content of our bits. So first, let's take wire A and split it in 2. We can plug both of these new ends into our first NAND gate. Let's think about what happens here. If we send a 0 down wire A, it splits and enters the NAND gate as 0 and 0. Because they aren't both 1s, the NAND gate should output a 1. If we send a 1 down wire A, it should split into a 1 and a 1. Because they are both 1s, the NAND gate then outputs a 0. Basically, by just splitting the wire, the NAND gate is perfectly flipping our signal, which means that we've basically replicated a NOT gate here. A 0 becomes a 1, and a 1 becomes our 0. Now let's do the same exact thing to wire B with our second NAND gate. So now we basically have 2 NOT gates from our original bits. Okay, and then to finish our circuit, let's plug these 2 signals into our third and final NAND gate. To prove that this works like an OR gate, we can consider a couple of cases. First, let's imagine that our starting inputs are 0 and 0. A standard OR gate should output a 0 here. Let's work through this circuit. Our first 0 goes into the first NAND gate and flips into a 1, and our second 0 goes into the other NAND gate and again flips into a 1. These 2 1s flow into the final gate, and because both inputs are 1, the final gate inputs a 0, which is what we expect. Let's try one more combination. Let's say input A is 1 and input B is 0. A standard OR gate should output a 1 here because at least one of the inputs is a 0. So input A goes into the top NAND gate and flips to a 0, and input B goes into the other NAND gate and flips to a 1. Now, a 0 and a 1 both flow into the NAND gate. So if you remember the rule here, a NAND gate only outputs a 0 if both of its inputs are 1. Since we have a 0 and a 1, it outputs a 1, which is again what we expect. So by arranging 3 NAND gates into a specific pattern, we've recreated the logic of an OR gate without actually needing to use an OR gate by itself. And the final topic we'll be covering in this video is reversibility. Let's take a look at the NOT gate again. If I tell you that the output of a NOT gate is 0, you can be 100% sure that the input was 0, because you can reverse the operation. But instead, look at the AND gate now. If I tell you that the output of an AND gate is 0, can you tell me what the inputs were? Well, you can't. The inputs could have been either 0 and 0, 1 and 0, or 0 and 1. 2 bits of information went in, but only 1 bit of information came out. Information was permanently lost during this calculation. Because you can't perfectly trace the output back to the exact inputs, an AND gate is what we call irreversible. When information is erased like this in a classical computer, it's actually released When information is erased like this in a classical computer, it's released as physical heat, which is partly why your laptop gets hot when it runs heavy programs. Later on, when we reach our quantum computing module, we'll see that physics places very strict rules on erasing information, meaning that we need to explore computation which is perfectly reversible. And that covers our foundation for classical computing. Data is stored as bits, bits can be written as state vectors, and those states are manipulated by logic gates. We've also seen that classical computers rely heavily on irreversible gates that destroy information. The next lesson will be taking these individual gates and arranging them into step-by-step instructions to solve specific problems, called algorithms. Thanks for watching, and I'll see you then.